Good morning. It's 9 a.m. here in San Diego, so we'll begin the webinar. Thank you very much for joining us today. So today's webinar is the first in a series of webinars that's covering searching and our MolScreen products. And also today's webinar is on RIDE, which stands for Rapid Isostere Discovery Engine. And so in this webinar, I will cover the method and some performance and benchmarking, and give a demo on how you can use it inside a web browser as well as inside the ICM software. So if you have any questions during the webinar, you can type them into the chat panel in the GoToMeeting dialog box, or you can ask a question at the end. You can raise your hand and we can open your mic so you can ask the question. If you have any questions after the webinar, please feel free to call me or email and we can answer your questions. Also, these webinars are recorded, so you can also view them on YouTube if you want to go back and see the webinar. So just a bit about MolSoft itself. The company was founded in 1994. We're based in San Diego in California. We have most of our customer base is pharmaceutical companies, biotechs and academia who license the ICM family of desktop modeling software. The company was founded by Ruben Abagayan, and the principal developers are Max Totroff and Eugene Rausch at MolSoft. And the method RIDE was developed principally by these guys at MolSoft. So the ICM family of software basically is ICM Pro. If you want to read what ICM stands for, it stands for Internal Coordinate Mechanics, which is the underlying method inside ICM, and the original papers are described here. So there are additional tools for homology modeling, ligand docking, cheminformatics, bioinformatics as well. So there's a whole suite of tools inside ICM. So as part of the webinar series, you can download the software and use it. There's an agreement to sign, and then you just go to our support site, you download the software, and you can send me that host ID that it reports when you open the software. Then I will send you a license key to activate the software. And it runs on Windows, Mac, and Linux. So RIDE is a fast 3D molecular similarity search method based on atomic property fields, which is referred to as APF, which we'll talk about in a minute. RIDE searches databases of compound conformers for molecules that are isosteric to the query. So they have similar 3D configurations and distributions of atomic properties. There is a CPU-based implementation of RIDE and a GPU implementation of RIDE. The GPU version, you can screen approximately 500,000 conformers per second on a single GPU, so it's very fast. So the method uses pre-generated conformers, and then the ligands are docked to the field basically using just translation and rotation. It's a completely new systematic search algorithm designed for speed from the ground up. It's high-level heuristics focusing search on the most relevant space. It uses pre-computed lookups and also a compact way of storing the data, and also evaluating concurrently many different poses. It's much faster on CPU, especially multi-core, but there's much faster than the original APF method. But there's also a GPU implementation, which is still order of magnitude faster. So how can you use RIDE? You can use RIDE for virtual screening, so you can efficiently screen giga-sized libraries, billions of compounds. You can use it for scaffold hopping, discover structurally novel chemicals based on a lead. You can also use it for hit follow-up. So if you have a lead compound, you may want to find other chemicals that have similar pharmacophoric binding properties. You can also adapt your search using some different options. So for example, you can weight certain properties of the molecule, and that can be modulated per atom to reflect the relative importance of certain regions of your query molecule. You can also use exclude volume. So basically you can have an envelope around your ligand, and that envelope will sort of represent the binding pocket for your search query. So the RIDE can be performed on a web front end, or inside ICM itself, using the ICM Pro software. So the ICM Pro software has a graphical user interface front end, which you can use, or you can use it on the command line using a batch script. And as I mentioned, RIDE runs. So RIDE uses the atomic property fields method. So basically APF, which is referred to as APF, it can be described as like a generalization of 3D point pharmacophores. So APF replaces discrete points by continuous property distributions. And it also replaces representation of chemical moieties with vectors of atomic properties that can be compared in a more flexible quantitative manner rather than binary matching. And these APF potentials can be visualized in ICM. It's just for visualization purposes. So you can see your pharmacophore. In this example, we have ciprofloxacin, which is it is a antibiotic, and it has it's quite useful for this example because it actually contains all seven fields that we use in APF. So we have hydrogen bonding donors, hydrogen bond acceptors, sp2 hybridized region, lipophilicity, size, and then also charge and electrostatics. So APF itself has many different implementations. It can be, it's the method underlying RIDE, and it can also be used for ligand superposition. So you could take a database, an SDF file of chemicals, and then superimpose them on each other, or superimpose those on a template 3D structure. You can also perform virtual screening, which is kind of similar to RIDE. You can also use the method for 3D QSAR as well. And it also has another application which is kind of outside of this webinar, but you can also use it to superimpose binding sites according to their pharmacophoric properties, and that's another paper by Max Totroff here at MolSoft. Actually, I should have pointed out in the previous slide that the paper here is the original description of the APF method. I can send that to you if you'd like to read it. So there's many different applications. So just sorry, one second. So how does it perform with other methods? There was a completely independent evaluation performed, and it's published here, comparing ROX, FlexX, MolSoft, which they refer to as ICM Sim, which is actually APF. And MolSoft's APF methods was shown to be the most accurate method for chemical superposition. So they sort of graded the superposition by 2 as excellent, 1's good, 0 poor. So in about 90% of the tests, ICM performed between excellent and good in chemical superposition. And ICM also performed very well for virtual screening enrichment as well, compared to others, particularly at the 10% enrichment as well as the 1% enrichment. So you can read that paper here, that's an example. Okay, So just so you can see what the APF fields look like, if you open ICM, you can go to our chemical editor. You can see here is the chemical editor button. If you click on that, you get like a panel to sketch. And in this example, you see you can use the tools here to sketch, or you can use smiles. But this example, I'm just going to use our chemical dictionary to find the molecule. Here. So we have it in 2D. You see that actually in this, as you sketch molecules in this editor, you can the properties are monitored on the fly. So we have Lipinski's rules as well as some other properties. It's going to undo them. So I'm just going to put this into a chemical spreadsheet, and then you have a chemical spreadsheet, and then we can right-click here and say chemistry, and then load and preserve coordinates, and then we can convert this this structure to what we call an ICM object. So we just right-click and we choose convert PDB chemical, and you can also assign charges. Just go OK. So then in the chemistry we can see the APF pharmacophore that we showed in the PowerPoint. You go to chemistry, APF tools, consensus pharmacophore, and then you can see the fields around it. So you can envisage that you can actually use more than one template. So you could superimpose multiple chemicals and then build the APF fields. And so all the tools, there's a separate webinar completely on APF. So if you want to go to YouTube, you can see that. But there's for superposition, there's tools here in the superposition menu to do multiple APF alignment, superimpose to a template, and the way to visual. This is just for visualization purposes. So you can see we have lipophilicity shown here, aromaticity, negative charge, positive charge, donor and acceptors. So these are the fields that you would dock or screen into using RIDE. Let's go back. So RIDE was benchmarked on the DUDE benchmark, which contains 102 target proteins from major drug targets. Approximately, there are approximately 200, on average, like 200 ligands per target, and approximately maybe like 10,000 decoys per active ligand, number of ligands. So, and the decoys are property matched to make it more challenging, really, for the method, so that they're going to have similar properties to the known binders. So it makes the ability to be able to discriminate binders from non-binders more of an achievement. And there's usually a ligand from an X-ray as well, which can be used for ligand-based screening from this benchmark. And the actual performance is pretty good on this benchmark. Over 2/3. This is the top 2% enrichment factor. These are the 100 receptors. So over 2/3 of them, you can has a very good enriched pretty well. There are some dubious ones here, which maybe the ligands aren't actually binding to the active site themselves. They may be allosteric ligands, but on the whole, for more than 2/3 of that benchmark, I see the RIDE performs exceedingly well. So I should have said in the previous slide that one of the drawbacks of the old APF method, although it performed very well on docking and comparison of the binding pose and also for enrichment, one of the drawbacks of the original method was it was pretty slow. So that was the reason really for developing RIDE itself. So if you can, we have here we are comparing RIDE, the new version, against the old way of doing flexible atomic property field screening. And there is very good reasonable, so the mean numbers and median numbers of APF flexible versus RIDE are pretty similar. So you don't lose a great deal by running RIDE compared to the slower APF screening method. And although sometimes the flexible APF screening does actually produce better alignments, it turns out that for ranking you do not really need to align the entire molecule perfectly, just the most important features. So that's why you still get very good performance between RIDE versus the old flexible APF method. So what kind of input do you have to put into RIDE? So the method can work with any set of pre-generated conformations. In ICM there are a number of conformer databases that we've already prepared, mainly from the bigger vendors such as Cambridge, ChemDiv and Enamine. But you can also prepare your own. If you have an in-house set, you can also prepare that. For most efficient processing, MolSoft designed a special database format based on SQLite, and the format is called MolT. You may be familiar with it with other ICM cheminformatics tools. So the space required is approximately 200 bytes per conformation, and it's 20 times more efficient storage method than SDF file. And it requires about 5 gigabytes per 1 million chemicals, with approximately 30 conformations per molecule. This format also provides efficient sequential and random access to the ID, and the database can either be generated by our method or by converting multiple confgen script, or by converting multiple external SDF files. So you basically take your SDF file and then convert it into this MolT format for input. So the algorithm systematically tries multiple rigid rotations. Once it has the conformer database, it calculates the APF grid score for each of the ligands in your database. It's you can run it in parallel on both CPU and GPU. As I mentioned, you can also fine-tune the query, so you can change the per atom contributions of different portions of the molecule. So you can weight certain regions as being important or not. And you can also apply what we call an envelope penalty to different portions of the molecule. So it kind of represents a binding pocket. I'll show you that in the demo in a bit. You can also provide, if you have a crystal structure, you can also provide the receptor or the PDB file as a way to exclude volume when you're searching. It can be implemented as an ICM script, so it can be run in the command line, or a background job from the ICM graphical user interface, or you can use RIDE in as a web backend. So this is a comparison of the speed of RIDE compared to other methods in ICM. This is a benchmark done on 1.5 million compounds, which contain 30 million conformations. For the CPU benchmark, we used Intel Core i7 CPU here, and for the GPU, a GeForce and a Tesla GPU were used. So the regular flexible APF, which as we reported it, is accurate in terms of alignment and superposition and enrichment, but it's pretty slow. To screen 30 million compounds, you're talking about 44 days. Rigid is probably half that time, rigid APF. But if you use RIDE, you can run it on the CPU. So if you have a standard ICM Pro plus VLS license, then you'll be running RIDE on the CPU. And you can do screen about 229 chemicals per second. So it would take approximately 1.7 hours to screen 30 million compounds. But if you have the RIDE GPU, so you need a separate license key for this, you can screen approximately 38,000 chemicals or chemicals per second in 48 seconds. So it could complete 30 million conformations in 48 seconds. So I was going to demo first of all the front end, web front end. So we have for the web front end, we have pre-generated databases from ChemDiv, Enamine, and Cambridge. And the front end uses the ICM JavaScript for viewing the results in the chemical spreadsheet. So you can, there's a webinar on ICM JavaScript as well on YouTube if you want to learn more about ICM JavaScript. So this way of implementing implementing RIDE is kind of designed for maybe the chemists in the lab. So they can load up the web page on their laptop or on an iPad or whatever, and then just sketch their molecule of interest, and then they can screen millions of compounds very quickly and get ideas for maybe how to improve that ligand in certain regions, or scaffold hop to another chemical series, for example. So it has a wide application. So the web probably we envisage being used by the chemists, and RIDE inside ICM is probably more designed for the modelers or comp chemists itself. So this gives a very user-friendly interface to RIDE. Okay, so we have this website, but it's currently protected by password, and we can provide that after the webinar if you get in contact. So so if you go to that website, you'll see that we have this chemical sketcher. So in our first example, we're going to look at Vioxx, which is COX-2 selective anti-inflammatory drug. So we have this chemical sketch. You could sketch the molecule, but again, I'm just going to use the chemical dictionary that we have embedded in here. So I'm just going to type Vioxx, and that displays the chemicals. So it has a sulfonyl group here, phenyl here, and many of these cyclooxygenase inhibitors have this sulfonyl or a sulfonamide group in this region. So we can sketch it. All these blue dots mean that each atom, they're all the same size, these blue dots. So it means all these atoms are currently weighted the same. There's no bias to any particular part of this molecule. So for this screening, we're going to set an envelope which will represent the binding pocket. And so to do that, we use the selection tools shown here. This button here would make selections. This is the dictionary that I just used. So I'm just going to select the whole chemical. So green is selection. And then there's a button here called Set Envelope for Selection. And this produces this representation of this envelope. So this basically represents the binding pocket. And I'll show later that you can actually open this up so you can start exploring additional groups that come out of the pocket. But at the moment, the way it's for this default example, we're going to penalize any group that may stick out here, that comes out outside of this envelope. And so now I'm going to screen 30 million compounds in during a live webinar. So we'll see how it goes. It should be about 40 seconds or something like that. We'll see. So you can just press right search, and you see it's busy superimposing these chemicals on the template. So in this web page, but you could have, if you had this in your company or in your lab, you can have your own internal database here that you could select, or your favorite vendor or whatever. This envelope penalty is a penalty score that if a group does stick out of the envelope, then it will get a deduction in score by this value. These buttons are for setting the envelope and clearing the envelope, which we'll show in a minute. And the 30 million screen is done. So you get this ICM JavaScript environment. So this is our original Vioxx structure. And then on the right-hand side, you have the panel. So we have here, obviously, the 2D structure. This L button column allows you to toggle the display on and off. You get a score. And the score in itself is not, well, you can rank by score, but it's probably better to look at the normalized score. So this is the score compared to the self score. So if you just take Vioxx and dock Vioxx to itself, it will return a score. So this is the normalized score. So you can rank by this score. I think by default it's ranked when you retrieve the results. They're obviously ranked by score to start with. So the best hit here, for example, is this one. So you can toggle it on and off, and you can browse through, or you can display multiple ligands on top of each other. So if you the ICM JavaScript has inbuilt a lot of visualization tools. So you can also in this menu here, you can change representations and other things as well. So so basically you can rank by score, and if you want to, you can change different ways of visualizing the panel. Show it in block form like this or whatever. So there's different options here. You can also export the hits you generated by going to save, shown here, and you can save it to Google Drive or locally to your machine. And you can make slides and other things, but that's a whole other webinar on ICM JavaScript. But in this example, maybe we know that this is a cyclooxygenase inhibitor, and most of these have this sulfonamide group here. But in the pocket for cyclooxygenase, there's actually space to grow your molecule from this phenol ring. So maybe in this example, we will try and modify the search query and allow us to find some additional groups that would stick out here. So to do that, we make a selection. And then you can say clear envelope for selection. So this will break the envelope here. So now when we do the screen, you'll get hits that come out here. So you press right search, and we could wait, or I've got them pre-calculated. So it should be less than a minute, but just for webinar purposes, I will show the results here. So yeah, so with that example, you should see, we see from this phenol ring we get additional hits like this extra ring here. Everything else sticks pretty much inside the envelope, but most of the modifications are going to be sticking out from this. It gives it so you get a different. So you can see quite easily scaffold hop doing this approach. So you just toggle through the results. Okay. So you may also want to give weights to certain parts of your query. So just to have an example for that as well. If we go back, it's going to select this and delete that one, and read in a drug used to treat Alzheimer's disease called Aricept, but I think it has the name donepezil shown here. So this is a acetylcholine esterase inhibitor, and from the it's clear that this region here is required for binding and possibly this ring and this charged nitrogen. But we can look for additional linkers between two points in this ligand. So so basically looking for a different core of this ligand. So at the moment you can see the blue dots indicate that every atom has the same contribution or weight. Sorry. So if we can just select everything and put the weight to 0 using this dialog box here. So you just go make a selection, and then here we have the weight here. So now we don't have any blue dots at all. But so if we want to find a different core between these two rings, we can select here and give it a weight of 1, for example. So you can see we have blue dots here, and this ring we could increase the weight threefold, and you can see the bigger dots. So now when we do the screen, we'll find these kind of points plus different linkers. So we'll scaffold hop away from this original ligand. So then, in the same way as before, you press right search and it runs. And so obviously you start to see when you do that, the original one is the green. The green was our template shown here, and you can see as you toggle through the results, we have a different kind of linkers throughout the hits. Okay. I should point out also you can save this as an ICB. When you save it, you can save it as an ICB file, which is the ICM binary format, and so then you can read it into the ICM browser or ICM Pro software, and it will give you the 3D structure as well as the hit list you have here, and so you can display it in ICM as well and share it. Okay. Just going to go back to the slides. So how can you try RIDE? As I mentioned, you can run it on. You can use it on our website, which is hosted by MolSoft. It's kind of limited access on demand, or you can run it locally on your machine, CPU or GPU. And as I mentioned, you can get a license key from us. The instructions should be in your email from GoToMeeting, or you can host a RIDE server on a local GPU, which is a good way of doing it. So we use this way of Docker, which basically contains the program. It's easy to install on the server, has all the libraries and everything embedded in this Docker file, and then you or your colleagues can access the GPU and the RIDE server from the ICM graphical user interface or from a web page. If you can have your own web page on your own machine. your own server. So how do you host the local ride server? You would require a CUDA enabled box with the Docker installed, and you can download it from this website. I can also provide that to you. It's also in the manual, and then you need to run the server and place the license key that I will send you into that directory shown here, and then you can access it from ICM GUI like this, or from a web page as we showed. So how do you run this inside ICM? So just get a clean ICM session. So when you open ICM, you get this window. We can initially look at the Alzheimer's acetylcholinesterase inhibitor that we were looking at before. So we can basically, what you need to do is sketch it. So we go here, type in the name of the drug, and just press enter. Sorry. Yeah, if I could spell. So you just click on there, and you could also read it in from an SDF file, for example, or you could search in ICM. You can also have a direct link to PubChem. You can search by name or using a search string or smile string. A drug bank as well is included. But just for this example, I'm just sketching it. Then I'll add it to a chemical table, chemical spreadsheet shown here. And then for ride, you could have one or more chemicals in your series superimposed. I'm just going to, in this example, I'm just going to use one. So I'm just going to convert this to, right click on the table and just load this as 3D, load and preserve coordinates. So now we can see that we have the chemical in 3D in the ICM workspace here. And it's currently a model. It says model here. So it's important to convert this to an ICM object. Yes.
Convert 3D. You need to convert it properly to 3D, not PDB chemical.
Yeah, I know. Yeah, that's what's just. Yeah, thanks, Eugene. Yeah, Eugene is the main developer. So it needs to be an ICM object. So we just go here, and then we go OK, and that converts it to an ICM object. And is that okay?
I mean, still the coordinates. You need to have proper 3D coordinates. That's just 2D object converted.
Oh, sorry. Okay, yes. Yeah, so, convert to 3D and optimize, and then sorry.
And charge it first from chemical table. Put the charge from the chemical table. Chemistry.
Yeah, this has a positive
you can
charge.
Do it from the menu. Edit, set formal charge. Okay, that's also.
So yeah, so.
Then convert.
Now it's, yeah, so now we convert it to an ICM object. So that's okay, right? That should be, is it?
No, you convert it again from the table. Right click on the table, delete everything in workspace and convert again.
Okay. Yeah. So the key thing here is the charge. So we need to chemistry convert 3D. And then, yeah, so now we have the charged nitrogen here. So now it's ready to go. Thanks, Eugene. Yeah, there was there. So now it's converted. You could obviously look at the APF consensus again, as we did with the other antibiotic earlier on. So you can see the property fields. So these are the property fields that we'll dock to, the APF fields. And so now we go to chemistry, and then we choose So for RIDE, we go to APF tools, shown here, and then we choose the option to go to RIDE search. And so we have, as we mentioned, there is the 3D conformer databases that we've already pre-prepared. So you can click this link here, and that will give you a web page. You see this is the multi format for different databases: Cambridge, Enamine, and ChemDiv. So you would select that option. You would browse for that file that you saved, and then you need to select the template or templates. So you just double click here to select. See, we selected it's blue here in ICM workspace, and green crosses for graphical selection. And then there's an APF cutoff, which is basically the score, the normalized score. So basically, so you won't get every single hit, you just get the top hits. If you don't get any hits, you may want to lower this cutoff a little bit to try and do that. You can, as in the similar thing with the web, you can also penalize atoms outside of the envelope of your 3D structure. And you can just go OK to run it. So you see there's two tabs here. There's one local, this will run locally on machine, or you can use the server setup, which you can set up using the Docker that provided. So yeah, so in this example, you could just go OK and run it. Just for demo purposes, I'm going to use the server, so I'm going to use the GPU base version. So once you've set up the server, you'd have to copy and paste the. So I'll show you in a second. So you have to copy and paste your server URL, so it'll be shown here, and then refresh the databases, and that will, you can see, sorry. So the databases are listed here. You can select them. These are the ones we have currently on our server. And as before, you have a template shown here, and you have exactly the same options for the envelope, the APF cutoff, and you can just go OK, and it will run. But I want to show you that. I'll show you the results of this in a bit. So an additional option you can use is called use excluded volume. So to use excluded volume, you need to read in the crystal structure. So we can search PDB to find some crystal structures with this inhibitor bound. So one way to do that, because we have a direct link to the PDB, we can just go to chemistry. I'm just going to add this column with the smiles string. Just 1 second. Okay, just going to add smiles here. I'm just going to copy that cell. Now I'm going to search the PDB by chemical, and then okay, doesn't work. Sorry, it should. Yeah. Okay, I can just read the PDB directly from the. So it's the PDB file is 604W, and then just go OK. And so that now we see that we have the crystal structure of this acetylcholine esterase, and the A chain is the one that we're going to use as the excluded volume. So we have the inhibitor bound here, so you can just double click and center on the inhibitor. So to set this up, we already have the original ligand. I'm just going to delete that ligand, and then it's going to delete the A chain, B chains of this PDB just for for clarity, and the other net atoms, molecules in the waters. And as before, we have so basically now we just have the receptor, which we can use as our excluded volume, and we have the ligand. We could take the ligand out, move it from object, and then convert it to an ICM object as we did before. So right click and choose convert PDB chemical. You can choose to auto assign formal charges if you haven't already set the charges, and just go OK. So now you can see it says ICM here, so it's an ICM object, and the PDB is an X-ray structure. So just one second. Yeah. So to use the excluded volume, what you need to do is you set up the server, you choose a database you want to screen, you choose the template molecule. So the template is, so here we have the two objects. This is the protein structure and this is the ligand. So you just double click here to select the protein, to select the ligand. But for to use excluded volume, you have to use this. So there's two different selections. There's this one, which is the green selection, and the one we need to use to select the protein to act as the excluded volume is this orange selection. So first you need to select it with green and then convert that selection to orange. Okay, and then we select the ligand here. So we have the template is the green selection. You see the green selection, and the excluded volume is the orange selection. So whatever you have is orange. And then you can just go, okay, everything's set up, it's ready to run. And I have the results of this one here. So in this exactly the same example, the receptor is used as excluded volume, and you get a hit list similar to the web as well. So you have the ligand and the score, normalized score. And then the advantage of doing it inside ICM is you also have the full range of cheminformatics tools, so you could build a multi-parameter optimization score as well on top of this if you wanted to, a variety of other things. So to view these superimposed, you can just click through the table or use the L button to display them. Yeah, so just wanted to, we'll end it there, but we have some questions that we can answer. I just wanted to thank you very much for your attention and for your interest in the software. Next week we're having a webinar on GigaSearch, and a few weeks after that it's a MolScreen webinar. So GigaSearch enables you to efficiently do substructure searching of giga-sized databases, and we developed it. Enamine are using it on their website as well, developed it with them. And then there's the MolScreen, which is a collection of more than 2,500 machine learning developed models using 2D and 3D chemistry, and that can be used for target identification, lead identification, ADME tox prediction, and other things. So these are our upcoming webinars. And you may have heard Eugene in the background, who bailed me out just earlier. Yeah, he's the main developer, so if we have some questions that maybe he could help with as well. So thank you for your questions. One of the questions, actually there's quite a few.